Assalamu alaikum. Dear students, today we will start the revision of some of the questions which we are going to solve in your second mid exams. So first of all, your first unit we are having deflection of beams. So the problem what we need to solve here is these notes we are having. So I will be explaining what problem which you are going to get. So first problem is finding out the deflection of the cantilever beam. See here what steps what we have. This is the problem, cantilever subjected to point load. So we need to find the deflection at any point in this beam. So what we do is, this is first from double integration method, is first of all we'll consider one cross section at a distance x from point B. So again at this point we'll be finding out moment. So what is moment? Moment is equal to force into distance. So at this point what is moment is force is P into x. This is the moment. So we got moment is equal to P into x. So we have to substitute this in the differential equation, and your differential equation is EI d square y by dx square is equal to mx. So in place of mx you have to put fpx. So after that we know we have to do integration for the above expression 2 times. So when we do first time we will be getting C1 first constant. If we do again integration we will be getting second constant. Now after this we have to apply boundary conditions to the above expression to find out C1 and C2. So what is the boundary condition? First applying boundary condition is at x is equal to L, dy by dx is equal to 0. See here x is starting, here is x is equal to 0. So x is increasing in this direction. So when it goes to this point, your x will become L. And this is the support A, where we know that deflection is 0 and also rotation dy by dx is 0 here. So the boundary condition is x is equal to L, dy by dx is equal to 0. So this we have to substitute in equation 1. So when we substitute this, we will be getting C1 is equal to minus PL square by 2. So again next boundary condition is again when x is equal to L, your y is also 0. That is deflection in downward direction at A is 0. So if you substitute this boundary condition in equation 2, this is equation 2. So what you get is again C2 you are getting, C1 you got C2. So we have to substitute C1 and C2 in equation 1 and 2. See, now we got this one. Substituting C1 and C2, the equations are 1 and 2. So this becomes EI dy by dx equal to px square by 2 minus pl square by 2. So this is called as slope equation. And again if you substitute C1 and C2 in equation 2, you will be getting one more equation, EIy px cube by 6 minus pl square by x by 2 plus pl cube by 3. This is called as deflection equation. So you got slope equation as EI dy by dx is equal to px square by 2 minus pl square by 2. This is slope equation. So dy by dx will become 1 by EI into px square by 2 minus pl square by 2. This is slope equation. Now again the deflection equation what we got here is this is slope equation. Deflection equation is y is equal to 1 by EI px cube by 6 minus PL square x by 2 plus PL cube by 3. This is deflection equation. Now if you are getting a problem like this, any problem with L is equal to 3 meters and P is equal to 50 kilonewton. Okay, now using this equation we can find deflection. For example, we need deflection at 1 meter from free end. 1 meter from that means your x is equal to 1 and your L is equal to 3 and your P is equal to 50. So you substitute x is equal to 1 here, P is equal to 50 and L is equal to 3. For example, if EI is given as something 1 into 10 to the power of 8 GPa, so you have to substitute this in place of EI. So when you substitute this, so what you will be getting, y at when you substituting x is equal to 1, you get the value. Substitute this. Again, if you want deflection at x is equal to, again this is 1 meter, but x will become 2. So that times y is equal to x equal to 2. You have substitute same thing, just change x is equal to 2 here. So what you will get in this equation, whatever x you substitute, you will be getting deflection at that point. So this is how you will, and if you want deflection at this point, here x is equal to 0. When you substitute x is equal to 0, you will be getting deflection at this point. Here, this is what we have done here. See, slope at free end, that is x is equal to 0. In slope equation, if you put, you will be getting slope. If you put deflection in x is equal to 0 in deflection equation, you got y is equal to PL cube by 3I. So this is how you find deflection in cantilevers using this double integration methods. Okay. Next, you have the next problem. This one. Same problem, but you have simply supported beam here. Simply supported beam subjected to UDL. What is the deflection at different points? So what you have to do, same procedure is there. The double integration method. You will be getting the slope equation and deflection. This notes is given to you already. Okay, that's why I am explaining here. So we got the same way as slope equation here and deflection equation. Now in the question, if you are asked to find out deflection at any point, for example 1 meter from support A, 1 meter from support A, that is x is starting from this point. So in place of x, you have to put 1. Length, whatever it is given, W is the UDL load, whatever it is given, you have to substitute here. So you will be getting slope. In the same way, if you put in deflection equation, you will be getting deflection. This is your second problem. And one more problem is given in this deflection is this one. Deflection of a cantilever subjected to UVL. Here also everything is same, but the thing is the load is in the form of UVL. At the end, fixed end, you are having W, and at the free end your intensity is 0. So what we have to do, again same thing, at a distance x you have to find out mx. See what we have done. This part is this one. So what is moment here? Force into distance. Now force is area, half into x into this y. This y, how to find out? Using similar triangles. See here, W by L, W by L, this is y, y by x, so y will become wx by L. So this you have to substitute Wx by L. This is your total load, and the distance will be from your base, it is 1/3 of x. So this is your mx Wx cube by 6L. So this you have to substitute in differential equation. Again, 2 times you have to do integration. Using boundary conditions, you have to find out C1 and C2. So you get the equation, this one, slope equation and deflection equation. So if your slope is asked, you have to substitute in slope wherever deflection or slope is asked. So for example, if you are asked at 1 meter from the free end, in place of x in the slope equation, you have to substitute x is equal to 1. So here what we have done, for free end we have found out the slope and deflection. So for free end your x is equal to 0. So you have substituted the x is equal to 0 in the slope equation, deflection equation. You got slope at free end is minus WL cube by 24 EI, and deflection at free end y is equal to WL to the power of 4 by 30 EI. Okay, this is your third problem which is given for the exam. Next we will go to unit 2 questions. Second unit, you are given a column to find crippling load. So what is the formula? P is equal to pi square EI by LE square. Now for any, what you are given a hollow section. See this hollow section, you have small d and capital D. So your I will become pi capital D to the power of 4 minus small d to the power of 4 by 64. This is I. E will be given, and the thing is you have to substitute LE. LE is based on end conditions. See here, if both the ends are hinged, your crippling load is pi square EI by L square, and your in respect the formula in respect with respect to LE is effective length. See, effective length LE is L for both ends hinged, and when your both ends are one end is fixed and another is free, then your formula will become pi square EI by 4 L square. If you put in LE, see, all the equations are pi square EI by L square. When you in the place of L you are putting LE. And what is LE? LE is given here. LE is equal to L for both ends hinged, and one is fixed, other is free, then you have to put LE is equal to 2L. If you don't want to use LE formula, then you can use this formula, actual formula, pi square E. Actual formula is for with respect to actual length, that is pi square EI by 4L square. Here L is actual length, but here LE is effective length. So when the both ends are fixed, 4 pi square EI by L square, and one end is fixed and other end is hinged, then you have to use 2 pi square EI by L square. These formulas you have to use. What based on your question, you have to see which formula you have to use. Okay, this is how you have to find out your crippling load or buckling load. Your next question is based on your Rankine's formula. Again, Rankine's formula is also based on is to find out the crippling load. So what is the formula is P is equal to sigma C. This is the notes. This is I am explaining you from the notes only. Okay, sigma C A by 1 plus A small a LE by K whole square. So in this from formula, sigma c is your crushing stress. Sometimes it will be given permissible stress also. Okay, so this is what and A is your area of the cross section. Small a is the Rankine's constant. This is also will be given in the formula in the problem. And the thing is, you have to find out effective length. Effective length is the same thing. Just know what I have shown you. If based on both ends are hinged, then LE will become L, and one is fixed and other end is free, then LE will become 2L. Based on the problem, you have to use LE here. And your K value is radius of gyration. You know what is K? K is equal to under root I by A. See here, LE is not the actual length. LE means effective length. Effective length will be based on your end conditions. So if the both the ends are hinged, directly you can use LE is equal to L. Okay. Like this you have to solve the problem based on your end conditions. And next, coming to the next problem is based on your secant formula. See, this is the secant formula. In secant formula, what will be asked is sigma value. Sigma is stress, maximum stress, which is equal to P by A plus P into E secant. I'll show you here. See, you will be asked to find out maximum stress in the columns using secant formula. See, secant formula, when you have to use when your E value is given. What is E? E is the eccentricity. Eccentricity means your force is applied with some eccentricity. So in this formula, your P and E, both the things will be given to you. So he see here P by A, P into E, secant LE by 2. LE is again effective length, under root P by EI by Z. So I'll explain you what is, how to solve this problem. So we have to change this in like this. P by A, to in calculator how to solve, you have to P into E divided by Z into secant when it comes, because in calculator you don't have secant value, thus you have to use cos LE by 2 under root P by EI. Now first what you have to do is, based on your end conditions, find out LE. P will be given E and I based on your cross section, and 2. So first you find out this one, LE by 2 under root P by EI. Then you find out this one, cos of LE by 2 under root P by EI, keeping the calculator in radians mode. Your calculator should be, when you are finding out this value, your calculator should be in radians mode. Then what you have to do, multiply this with Z. What is Z? Z is equal to I by Y. What is Y? Y is equal to, for example, if circle is there, from center to the extreme fiber, this is your y will become d by 2. Like this you find out z. So then after finding out this one, putting the calculator in radians mode, multiply this with the z1. After doing this, then you go for remaining part of the problem, that is p into e by whatever you are getting the result plus p by a. This is only for the calculation part. So what you will be getting, maximum stress. When if the problem if it is given minimum stress, what you have to do is in place of plus you put minus. So this is how you have to go for the secant formula. Coming to the third unit problem, what given in the question paper is, you have to use theorem of three moments, that is Clapeyron theorem, to find out the moments. And the problem is like this type. We are given a continuous beam, one end is fixed, other one is simply supported. You need to find out the moments at different points. So if you want to apply Clapeyron theorem, that is three moment theorem, so what we have to do in this type of problems I explained in the class is, we have to assume one imaginary, see like this, an imaginary span with that actually it is zero span. Then we have to apply three moment theorem, that is for a1 a b we have to apply the theorem first. Next we have to apply the theorem for a b c. So when you apply the theorem for a1 a and b, so you will be getting one equation. Then when you apply the theorem for a b c, then you will be getting one more equation. And what we know is, for this type of problem we are having two unknowns, that is ma is unknown, mb is unknown, and at c we know the moment will be 0. So because of c moment is 0, ma and mb is two unknowns. For two unknowns we need two equations. So for two equations, for that reason we have to assume one zero span, imaginary span. Then we have to apply the three moment theorem. So in the same way, we have assumed zero span here. Applying the theorem of three moments for the span a1, a and ab, we have this one. See. Here we have applied this. So when we apply this theorem, so you know all these things, we will be getting one equation, 2ma plus mb is equal to 24. This equation we will be getting by applying for the a1 ab. So next we have to apply the theorem of three moments for span ab and bc. So when you apply this theorem for this one, so you will be getting one more equation, that is ma, you get the equation as 2ma plus 8mb is equal to 96. This is the second equation. This is one equation, this is the other equation. ma and mb are unknown, two equations are there, two unknowns are there. So when we subtract this one equation from the other, so you will be getting one unknown, that is mb will be getting, from mb will be getting ma. So this is how we calculate mb and ma. So after doing this is how ma is 6.86, mb is 10.28. First we will draw this one. This is the simply supported bending moment diagrams. So this part is a neglected part. This will be your actual bending moment diagram. So from this, if you want to find reactions, what we have to do, from any point we have to consider all the forces either left to the beam or to the right of the beam. Then we will be getting the reactions RA, RB and RC. So here I'll show you how we will do the reaction part. So this is the B, A, C. You have UDL here. This is RB, RC, and this is RA. So MA we got a 6.86. This one is 6.86, and MB is 10.28. This is clockwise, this is anti-clockwise. This is again 10.28. Now I will take moment about B to the left of the section. If we take right of the section, we will be getting RC. If we take left of the section, we will be getting RA. So anything we can take. For example, if we take right of the section, see here, moment about B, considering RHS, right hand side. So what you will be getting, see here, RC into this L is 4 meters. This is anti-clockwise. Okay, so this is also anti-clockwise. This is anti-clockwise, this is also anti-clockwise. So plus 10.28, and this force is again clockwise. So I'll take minus. What is the force? UDL is 6 kilonewtons. 6 into 4 is the total load, then 4 by 2 is equal to 0. So what you get is RC 1 by 4 6 4s are 24 into 248 minus 10.28. This is where you get 9.43 kilonewtons. In the same way, if we consider from this point to the left forces, so you will be getting RA, then you also get RB. RA is we are getting 11.14, and RB you are getting as total 27.43 kilonewtons. This is how you have to do your seventh problem. Next problem what you are having is a fixed beam problem. See, we have done this one, fixed beams. Fixed beam for A also fixed, B also fixed with point load. What is MA, what is ME? Same procedure we have done, double integration method. For any point we have considered a cross section, we have found out the MX. Now this MX we have substituted here. We got MX. This MX here is RA into X minus MA. See here, RA into X, and this is MA. This we have then minus W into X minus A. This total you have substituted in this differential equation. From this we have done using quantity conditions, we got MA and MB. MA is anti-clockwise, W B square A by L square, MB is equal to W A square B by L square. Okay. Again one more problem is with UDL. With UDL we got MA is equal to WL square by 12, WL square by 12 for left and right side. So what problem you will be getting is this one. See, like this problem you will be getting fixed beam with UDL and point load. See, for example, if we segregate this one, with point load and UDL. So point load you are having WL by 8 anti-clockwise, this clockwise, this will be minus, this will be plus, and for UDL you will be having anti-clockwise, clockwise. So MA will be this plus this one. See here, MA point load is 50, so length is 6, so WL by 8 for point load plus WL square by 12. W is the UDL is 9, so 9 into 6 square by 12. This total will be your MA. The same way MB will be this plus this one. Now if we are having point load, because this is central point load 3 meter, 3 meter. If your point load is somewhat different, so you have to use different formula. See here, the point load is not in center, so for that you have to use WB square A by L square for MA and WS square B by L square for MB. And your next problem is, you will be getting problem like this. This is an indeterminate structure, so you need to find out forces in all the members. So because it is a multiple choice, you will be asked for finding out any one of the member. So this is for this problem. I have already given the notes for you, so I will be attaching the explanation for this with this video. Okay, so this is the problem. Here it is hinge, it is roller support. So external static indeterminacy ds, first we will do internal. ESI is equal to m minus 2j plus 3. M is 1 2 3 4. Just now we have done this. 6 1 2 3 4 5 6 minus 2j 1 2 3 4 4 to the 8 plus 3 9 minus 8 is equal to 1. Your internal DSI is equal to 1. External, you have two reactions here, one reaction here, so 3 minus 3 will become 0. So externally we don't have indeterminacy. Indeterminacy is because of internal only. So the first step is we have to remove the one member, because only we are, if you are having 5 here, then it will be redundant, but because 6 members are there, so we have to remove one member. So we will remove one member. So first step is we have to find all the forces because of external force for statically determinate structure. So when you take reactions, this is RT. So you have here, we have 4 meter, theta will be 45 degrees. So RD into 4 is equal to 10 into 4. RD is equal to 10 kilonewton. See, if this is 10, so you will be having, this will be 10, and here downwards it is 10, so upwards also will be 10. Two reactions are coming because this is hinge one reaction because it is roller support. So we'll start the problem with, you can see joint C. and C. Tan C. This is B and this is D. Sigma V is equal to 0. 10 plus FCB. Ten is equal to FCB. So FCB is equal to 10 kilonewtons. CB, BC, CB is 10 kilonewtons. And sigma H is equal to 0. FCD is equal to 0. FCD is 0. So we'll go for the next joint. Joint D. This is 10. This is towards C, B, A. So you have 10 plus F DC plus F DB cos theta. FDC is 0. So FDB is equal to minus 10 by cos theta 1 by root 2 become root 2. Minus 10 root 2. FDB is minus 10 root 2. Likewise, sigma V is equal to 0. FDB sin theta plus FDA is equal to 0. FDA is equal to minus FDB sin theta. FDB is minus of minus 10 root 2 1 by root 2 become plus 10 FDA. Next we go for joint B. Joint B is away from joint B, C, this is D, this is A. We want this one, so we go for FBA plus FBD cos theta is equal to 0. FBA is equal to minus FBD cos theta, where FBD is minus 10 root 2 minus 10 root 2 1 by root 2. Again it is plus 10 BA. Here AC we don't have, remember it is 0. So next what we have to do is, next step is to apply this is, we are applying away from the 1 kilometer. This is A, C, B, D. In AC we are applying 1, already known. Because of this 1, what is happening to all the forces we have to find out. So coming to joint C here, again here, we go vertical, FBC plus this is FAC or CA. CA sine theta is equal to 0. FCA is equal to 1. So FBC is equal to minus of 1 by root 2. So it is minus 1 by root 2. FBC. FBC is minus 1 by root 2. This is sigma V. Now we'll go for sigma H is equal to 0. FCA cos theta plus FCD is equal to 0. So FCD is equal to FCA minus 1 by root 2. Minus 1 by root 2, again FCD. We got this one, this all the forces. Joint B. So you have like this. C A this is B. Now sigma V is equal to 0. FBC plus FBD sine theta is equal to 0. FBD is equal to minus FBC. FBC is FBC plus FBD sine theta. We want FBD. FBD is equal to minus FBC by sine theta. What is FBC? Minus 1 by root 2. Minus into minus. Minus 1 by root 2. 1 by root 2. So we have 1. FBD is equal to 1. We got now sigma H is equal to 0. FBA plus FBD cos theta is equal to 0. FBA is equal to minus FBD cos FBD is 1. When you go that side, it will become minus 1 by root 2. FBA is equal to minus 1 by root 2. In the same way we go for joint D. Away from joint, away from joint, away from joint. And this is C, B, A, D. We want DA. FDA plus FDB sin theta is equal to 0. FDA is equal to minus DB. DB is 1 by sin root 2. 1 by root 2. FDA is cancel root 2. Again minus 1 by root 2. This we got. Now lengths. Each length AB is 4 meter. Everything is BC is 4 meter, CD is 4 meter, DA is 4 meter, DB. So DB will become 4 meter, 4 meter. This is D, this is B. Sin theta is equal to 4 by hypotenuse. Hypotenuse is equal to 4 by 1 by root 2 will become 4 root 2. Here dB is equal to 4 root 2. 4 root 2, 4 root 2. Now what we have to do? PUL. PUL. Multiply this by AE. AE. Here area and Young's modulus is not given, means that area for all the members and Young's modulus for all the members is same. So we will take this into this into this. So what we get? 40 minus 40 by root 2. Again minus 40 by root 2. This will become 0 minus 40 by root 2 minus 40 into 2 will become 80. This will become 0. This is u square L by A. U square is this one, is this is u square into this one, and 4 by 2 will become 2. Again this by this into 2, 2 here again, here also 2 again. This will become u square by u square into L. This will become 4 root 2 and this will become 4 root 2. So now what we have to do is we have to add all these things, this and this. So now we have to find the actual forces here. P is 10, R we got as 8.54, 8 this plus 8.454 into this one minus 1 by root 2. When we do this, we will be getting 3.96. Here also we get 3.96. Here minus 6.04 and we get 3.96 again, minus 5.6 and we get, see here, P is 0 here, and multiply with 8.54 you get 8.54. These are all in kilonewton. This is how we do the calculation for all the forces using Cauchy-Green's second theorem. Cauchy-Green's second theorem is used for indeterminate structures. Let's see, here we are having 3 reactions, and for roller support 1 reaction. Total we are having 3 plus 1 is equal to 4 reactions, and we are having 3 equations. 4 minus 3 is equal to 1 is the degree of static indeterminacy. Likewise, if we are having frame like this, both we are having hinge and also hinge. So we are having hinge means 2 reactions. Here also 2 reactions. Therefore, total 4 minus 3 again 1. So in this type of structures we are going to analyze using energy method. So let us start the problem. When we solve the problem, we'll understand how we are going to do the analysis. The problem is fixed support here, roller support here. We have 20 kilonewton, 2 meter, 2 meter. And here we have horizontal force 10 kilonewton, 1 meter here, 3 meter. Now we have to do the analysis. First we will find degree of indeterminacy, static indeterminacy. ds is equal to, total reactions are 3, this is A, B, 3 plus roller support 1. So we have 4, and 4 minus 3 will become 1. ds is 1 degree of indeterminacy. So how to solve this problem? First what we have to take, we have 4 reactions. So we have to remove 1 reaction. First remove the redundant force. 3 plus 1, 4 are there. One force we have to remove. The example what I will tell you how we will solve. In prop cantilever, what we have done, we have removed this one, RB, this is RA. Removing RB, it was like this. Then we found out downward deflection at B. Then what we have done, removing the forces, we have applied only RB. Because of RB, what is the upward deflection? At B. Then we have equated this and this one. Delta B1 is equal to delta B2. From this we found out RB. Same procedure we have to follow here. First what we will do is, in this frame we will consider RD as redundant force. So we have removed RD. Here we are having RD, we have removed. Now this is the frame. We will find downward deflection at D. We have removed RD. So at this point, what is the delta D? We'll find out because of external forces. This is first step. Then what we'll do, next step is removing external force and applying redundant force RD and finding upward force at D, that is delta D dash. Removing external force and applying redundant force RD and finding upward force at D, that is RD. That is what we do is in this frame at D we are applying RD. Because of RD, what is the upward deflection? Delta D dash. We will find out this. Then next step is we will equate upward deflection equal to downward deflection. Delta D dash is equal to delta D. From this we find out RD. This is the procedure. What will do, we will remove the redundant force RD at this point, and because of external force, what is delta D we will find out. The next step is we will apply RD at this point, and what is the upward deflection delta D dash we will find out. We will remove the external force. Then we will equate delta D dash equal to delta D. From this we will find out RD. The same procedure how we have done for the prop cantilever. Now I will start the problem here. So first we have to find out downward deflection. (10 kilonewton) and it is 20 kilonewton at this point. This will be delta T. So how we will be doing, using the unit load method. What is the unit load? We having portions. We divide the frame into portion A, B, C, D, this point as F, this point as E. So we'll start the problem here. First thing is we have to divide the whole frame into portions. So we are having portion is DC, CF, FB, and we have BE and EA. So I'll write the portion here. DC, CF, FB, BE and EA. So we'll write the origin. Origin means from where. For DC we'll start from D. For CF it is C. For FB it is F. B it is B. And EA it is E. This is the starting point. And the limit for DC it is from D to C. What is the length is 4 meters. So the limit is 0 to 4. And CF it is 0 to 0. This is 2 meters. 2 meters. This is 4 meters. 1 meter. 3 meters. And you have this as I, and for beam it is 2I. CF it is 0 to 2, and again it is FB is 0 to 2, and B is 0 to 1, and EA is 0 to 3. And EI values, so you have EI as EI. For FC we are having 2I, so EI will become 2EI. Even for FB it will be 2EI, and BE it will be EI, and EA it will be EI. Now what is capital M? Here capital M is the moment because of external load, and small m is because of unit load. For each and every limit we will have to find capital N and small m. So we will start from first DC. See, this is D, this is C. So your limit is from 0 to 4. See, for example, if you take section here, this is X. From here to here it is X. So what is capital M? We don't, because there is no force acting from here to here limit, your capital M will become 0. And small m, what is small m? You have to apply unit load at joint M. Now here I will be applying unit load 1 kilonewton. Again, if I take a section from 0 to from D to C, because the load is acting along the line, you don't have moment M, that will also become 0. This is for DC. Okay. Next we will go for CF. DC. Now for CF, so I will draw the figure. This is F, this is C, this is F, and this is the column. Now again, if I take cross section this here, from here to here it is X, but again we don't have any force here, so capital M again it will become 0. and we apply unit load at this point, 1 kilonewton, and your cross section is this one. So small m will be 1 kilonewton into x. So it will be 1 kilonewton, and we have the direction clockwise. We will take x here. Okay. For DC is over, for CF it is over. We have to go for FB. I will draw the figure here. This is D, this is C, this is F, this is B. So FB, your limit is 0 to 2. From here to here, this is the limit. So your x will start from this point. This is your x. So what is the load here? Here we are having 20 kilonewton. So now if I take moment here, it will be 20 into x. So now your capital M will become 20x. And now we are going to remove this load, apply the unit load. This is your F, this is C, this is D, this is your B, your X is here. Now what is the movement small m here? Now 1 kilonewton is here. So this will become 1 kilonewton into this distance. This is 2. The total will be 2 plus x. 1 into 2 plus x. And you have clockwise. This is over for FB. And coming to this is FB. This is CF. This is DC. Now coming to BE. What we have framed like this. This is D, C. We have 20 kilonewtons here. Yes, now BE. This is your B. This is your E. Now your section will be from B to E. This is your X. Now here you want moment. What is the moment here? We know this is 2 meters. So your moment is 20 into 2. 20 into 2. And now again you have to apply unit load at D. This is your D, 1 kilonewton. Now your cross section is here. At this point, what is the? So we have this is 2 meter, 2 meter. D, C, F, B. Your E. From here it is 1 into this distance is 4. So your small m will become 4. This is for B is over. Now we will take your last limit, that is EA. So you have a frame, total frame. Here E is here and this is A. So your cross section is here. From this point you want to know what is the, this is 20 kilonewton, this is 10 kilonewton. So what is the moment here? So this is 20 into 2 plus 10 into x. This is 20 into 2. This is clockwise. Again this is also clockwise. This is 10 into x. So you have 20 into 2 plus 10x. This is your capital M. And you apply unit load (1 kilonewton). This is your E and this is your x. Now if you want the moment M, this is 1 into 4. This will become 4. This is how we got M, small m, for all the limits. Now we have to do the integration part using the above, because we know your deflection is delta. Your delta is equal to integral capital M small m dx by EI. This is the unit load formula. Same we have to do for each and every point here. So we will start. Delta is equal to, your first limit is DC and your limit is 0 to 4. 0 to 4. 0 to 4 is the limit, and your M is also 0, small m is also 0. This is 0 into 0 by EI dx. This is for DC. Next CF plus, your limit is 0 to 2. 0 to 2 and your capital M is 0 into x. 0 into x small m by EI is 2EI. You have 2EI here. Plus, next is FB. FB limit is 0 to 2 and your capital M is 20x and your small m is 2 plus x into dx by, it is 2EI, plus again B is, your limit is 0 to 1 and your small capital M is 40, 20 to 2 into 4 dx by, you have EI here, plus last limit is, you are having 0 to 3 and capital X into small x is 20 into 2 plus 10x whole into 4 dx by EI. We have to do simplification for all these things. So this way we have to do integration here. Say this is 0, this will be also 0. This we are doing simplification here. Now integration is 40x will become 40x square by 2. 20x square will become 20x cube by 3. 160 will become 160x. And here 160x plus 40x square by 2, 0 to 3, 0 to 1, 0 to 2. So when we do the simplification, we will be getting 1 by EI 66.67 plus 160 plus 480 plus 180. This comes to 886.66 by EI. This is your delta D. Because of external load. Upward, downward deflection at D. Now next what we have to do is, for the same thing, apply reaction at D, that is RD, and find upward deflection, removing all external loads. So what we have to do is, for this frame, at this point we have to apply RD, and again we have the same procedure, D, C, F, B, E, A. So what, this is the RD is the now the force. So we have to apply RD and also upward force to be applied here. No, we have to apply force here. This will be upward force. This is RD. Because of this we will be getting capital M, and again we have to apply unit force 1 kilonewton at D, and because of this we will be getting small m. Then again we have to use the formula of unit load method. Capital M will be because of RD, and small m will be because of 1 kilonewton, and the same procedure we have to follow. Now I will calculate the same procedure here. Now your capital M is coming from your RD. Now you are having, see, DC is there. Here you will be having the cross section. So because no length, your capital M will also be 0, and your, because of 1 kilonewton, small m will also be 0. And your next is your this portion is over, thus we will go for FC. Now here, if the section is here, your capital M will be RD into X. And small m will be, because F, this is E, small m will be 1 kilonewton into X, this X. Okay. Now for portion FB, here is the cross section will be here, from here to here it is X. So total will be 2 plus x into RD. RD into 2 plus x. And your 1 kilonewton will be again 1 into 2 plus x. Now for next BE, your cross section will be here. From here we have to go for RD. This length is 4. So 4 RD, and your small m will be 1 into 4, it will be 4. And for this E and A, again it is 4 into RD, and a small m will be 4. This is how we will be getting the value. Now your delta D dash, this is upward, will be 0 to 4 0 plus 0 to 2, this into this is RD into x square, by we have 2EI dx, plus here the limit is 0 to 2 and you have RD into x plus 2 whole square by 2EI, and this is limit 0 to 1, 4 into 4 is 16 RD dx by EI, and it is 0 to 3, 4 into 4 is 16 RD dx by EI. So we have to do the integration for this. Delta dash D will become, this is 0 and this will become RD x cube by 6 EI 0 to 2 plus, when we do the whole square for this will become RD, you can take common, RD by 2 EI common, x square will become x cube by 3, 2 square is 4, will become 4x plus 2 into 2, 4x will become 4x square by 2, 0 to 2, and this will become RD by EI 16x 0 to 1 plus RD by EI 16x 0 to 3. If we take common RD by EI, from 2 cube is 8 by 6, again this will become 8 by 6, this will become 4, and this will become again 4 plus this will become 16, this will become 16 to 3 48, it will become 74.66 RD by EI. This is upward deflection. Now we will equate downward deflection equal to upward deflection. That is delta D is equal to delta dash D. So what is delta D? Delta D we got 886.66. 886.66 by EI, and this we got as 74.66 RD by EI. From this, RD will become 886.66 by 74.66, which is equal to 11.8 kilonewton upward. This is your redundant force. Now remaining forces how to find. We have come to know this force, which is equal to 11.875 kilonewtons. Now at this point we are having 20 kilonewton, and we have here 10 kilonewton. Now we need to find also R A. This is A, B, C, D. So upward force is equal to downward force. So 11.87 plus RA is equal to 20 kilonewtons. That implies RA will become 8.125 kilonewtons. 0.125. Now we also want moment at A. Moment at A. So we'll find here. This is 3 meter clockwise. 10 into 3. Again this is plus 20 into this is 2 meter clockwise. Then moment at A will become 10 into 3 plus 20 into 2, and this is minus 11.875 into 4. This will come as 22.5 kilonewton meter, and your direction will be anti-clockwise. Moment at A. This is how we will solve the problem.